Welcome to the 2022 Shipyard Seminar and Knowledge Sharing Session. My name is Ian Isak Kumaraswamy, and I work as a process engineer in the Marine Installation Department here at MAN Energy Solutions. My primary tasks are focused on the auxiliary components of our dual-fuel engines. I specifically focus on our methanol and LPG engines, working closely with suppliers of auxiliary components and in correspondence with engine builder, shipyard, classification society, and vendors. Today, I will be guiding you through this presentation. This session covers the methanol engine, or as we also call it, the ME-LGIM-W engine. Besides this presentation, you will receive an invitation for the follow-up Q&A session, of which I also will be present. We look forward to seeing you there, and we are glad to answer any questions that you may have. The agenda of the day is seen here, divided into 5 main points. The first point is the dual fuel overview. I'll take you through an overview of MAN Energy Solutions dual fuel portfolio. Secondly, we will speak about the LGIM-W engine, take a closer look at specifically the engine, components, and piping that are relevant for the methanol engine. The third point on the agenda is the LGIM-W Tier 3 solutions. Here I'll be talking specifically about the Tier 3 solution that is relevant for methanol, which is water. The fourth point on the agenda is the auxiliaries and installation. Here I'll be talking most importantly about the auxiliary components and subsystems that are necessary in order to live up to the requirements and inlet conditions set for the engine. I'll be talking about the subsystems. I'll also go into the sequences. I'll take you through a startup scenario, a normal operation scenario, and a stopping scenario. Finally, I will show you how you have access to the installation documentation in order to find the specifications that we set for the engine. The first topic today is the dual fuel overview. Our two-stroke dual fuel technology portfolio is divided into 2 main groups depending on the injection type. Gas injection type is seen on the right, and liquid gas injection type is seen on the left. The liquid gas injection type is abbreviated to LGI, which you can see adopted into the names of our LPG, methanol, and ammonia engine respectively. LGIP stands for liquid gas injection propane, LGIM stands for liquid gas injection methanol, and LGIA stands for liquid gas injection ammonia. Furthermore, you will see that for the LGIM engine, we also have an LGIM-W option, which is if you choose to include water as your Tier 3 technology. As mentioned earlier, my scope of work is within the LGIP and LGIM engine, as well as the LGIA engine, which is in development. However, in this presentation, we will be focusing on the LGIM engine, including the option with water, also called the LGIM-W. On this slide, you can again see the two-stroke dual-fuel technology portfolio split into injection type as well as fuel types. On the left, you can see our gas injection engines, starting with our LNG-fueled engines, MEGI and MEGA. Furthermore, you can see our ethane-fueled engine, called the MEGIE engine. On the right, you can see our liquid gas injection engines, starting with our methanol-fueled engine, ME-LGIM, our LPG-fueled engine, ME-LGIP, and finally our ammonia-fueled engine, ME-LGIA. This last engine is under development, as mentioned before. Some of the main advantages of using methanol as a marine fuel are listed here. We have a proven engine design available today with more than 100,000 running hours on our methanol engines and counting. Furthermore, with methanol, we see a reduction in CO2 compared to fuel oil or MGO. And one can argue that if produced from biomass or power to X, it can be considered carbon neutral. Storing methanol is also easy. Due to methanol's chemical composition, it remains liquid at ambient conditions. It is not necessary to take boil-off gas into account, and no cryogenic equipment is needed. It can be stored in integrated tanks at ambient temperature and pressure. Finally, methanol systems require a simple supply system. We only require 13 bar supply pressure. On this slide, you can see a historical timeline of our dual fuel engines and development. Everything from our first MEGI tests at our test facility in Copenhagen, also called the Research Center Copenhagen, as well as retrofit projects, shop tests, and sea trials of all our dual fuel engine types. Often, testing new engine sizes and types is made available due to good collaboration with engine builders and shipyards for shop tests as well as sea trials. Specifically for our LGIM methanol engine, you can see some of the bigger milestones here. So far, we only have our LGIM engine in service in methanol carriers. Typically, a 6G50 LGIM engine would be used here, where 6 is the amount of cylinders and 50 stands for the bore size. However, due to the last year's extensive focus on sustainability and meeting emission requirements, the methanol engine has now been ordered for several other vessel types. We have seen orders as large as approximately 50 megawatt engines for container vessels. These orders are much larger than the typical 7 megawatt LGIM engines ordered for methanol carriers. You can see this on the right with the introduction of the G95 LGIM engine, a 95 bore engine. This, of course, creates new challenges, but we have been able to, within the last year, include 4 new bore sizes for our LGIM engine, as our design departments are up to the task. The next topic on the agenda is the LGIM and LGIM-W engine type, where I will focus on specifically methanol components on the engine. The methanol engine is based on the proven high-efficiency two-stroke diesel cycle, a concept we have a lot of experience with. Specifically for the methanol engine, we have 13 bar supply pressure, which reaches approximately 600 bar injection pressure using hydraulic oil. The methanol temperature to engine should be 25 to 50 degrees Celsius. It is necessary to apply pilot oil to ignite the combustion. The pilot oil amount is 5% using any compliant fuel. The methanol engine can operate on methanol in the range 10 to 100% engine load. This is a close-up of some of the components located on the cylinder cover, relevant for the methanol engine. There are components for hydraulic oil, pipes, accumulators, valves. 300 bar hydraulic oil is supplied from the hydraulic oil system, and it raises the methanol to injection pressure of approximately 600 bar in the fuel booster injection valve. The fuel booster injection valve, also called the FBIV, is designed to boost the methanol to reach injection pressure. Furthermore, it is designed to minimize the risk of hydraulic oil and methanol potentially mixing. A sealing oil system is used in order to mitigate this. The drained and used sealing oil is then recirculated to a separate sealing oil tank in the sealing oil unit mounted on the engine, which handles a potential methanol contamination in a safe way by ventilating and monitoring it. You will also see dedicated methanol components, such as chain pipes mounted on the adapter block, which is part of the gas block. In the following, you will see some more of these methanol components. We try to indicate the gas components or methanol components with the color yellow. As you can see, the FBIV is shown on the top left, then the control blocks and the methanol chain pipes. The sealing oil system is seen on the right. You can see the location of these methanol components on the engine by following the red arrows from the components close-ups. The methanol chain pipes supply and return methanol from the main engine inlet flange from gas block to gas block. The chain pipes are of double wall type and they are ventilated with minimum 30 air changes per hour. The gas block is divided into the control block and the adapter block. The red line marked here indicates the control block on top and adapter block below. The control block is mounted on the cylinder cover. It receives methanol from the adapter block and directs it to the FBIV for boosting and injection. The adapter block is mounted on the control block. It supplies and returns methanol from gas block to gas block in the starting, operating, and stopping sequences of the engine. The next topic on the agenda is the Tier 3 technologies, specifically the water and methanol technology, which is only applied for the methanol dual-fuel engine. The typical standard Tier 3 technologies as you know them are EGR, exhaust gas recirculation, and SCR, selective catalytic reduction. Specifically for the methanol dual-fuel engine, we have, however, removed the SCR technology from the Tier 3 portfolio. This was necessary in order to optimize our methanol Tier 3 portfolio when introducing water and methanol as a new Tier 3 solution. Using methanol itself as a fuel includes a NOx reduction by 30 to 50% without any further NOx abating system. We have researched and tested the possibility of mixing water with methanol. Mixing water with methanol reduces the combustion temperature, and therefore NOx emissions are not created to the same extent as in a combustion without water. Mixing the correct amount of water will ensure NOx emissions meet the Tier 3 requirements. We have found that water mixes well with methanol. Therefore, a simple injection of water into the methanol supply line will suffice. It is necessary to ignite the mixture using a pilot oil in order to reach a proper combustion, as it is for regular methanol operation without water mixed in. For injection of the pilot oil, we use the fuel injectors. On this slide, you can see a system overview without water as a Tier 3 technology. It was necessary for us to consider where the most optimal position was to include the water injection. We chose to insert the water in the fuel valve train. And why in the fuel valve train? The FVT includes a double block and bleed valve system, valves 801, 807, and 802, to separate the methanol high-pressure supply from the consumer. The consumer is the engine. The block valve 801 in the methanol line can also be considered a master valve. This idea was also adopted for water. By separating water from the methanol with a double block and bleed valve configuration, the water injection unit does not need to be X-proof and can be placed in the engine room. This was a more cost-efficient option for the shipyards than if it were to be X-proof. Furthermore, the FVT is a controlled component. MAN engine control system can control the injection of the water. The next item on the agenda is the auxiliaries and installation. First, I will give you an overview of the auxiliary components related to the methanol engine and systems. Here you can see an overview of the different subsystems related to the methanol engine. On the left, you can see the methanol fuel service tank, which holds the methanol dedicated for engine operation. The methanol is stored in the fuel service tank at ambient pressure and temperature conditions. Below the service tank, you see the low flash point fuel supply system. We also call this the LFSS, and it ensures correct conditioning of fuel according to engine inlet. This is regards to pressure, temperature, and filtration. To the right, you will see the nitrogen system. The nitrogen system ensures sufficient N2 for purging engine and nitrogen for purging fuel supply system. On the top right, you see the fuel valve train. The fuel valve train has the purpose of separating pressurized methanol from the engine. And to the left of the fuel valve train, you see the water injection unit. The water injection unit has the purpose of filtrating and pumping the water from the engine room to the FVT at the correct pressure. I will now go through the mentioned and most important subsystems that ensure proper methanol running according to our specification. The purpose of the fuel supply system is to ensure that the delivered methanol is living up to the specified requirements regarding pressure, temperature, and filtration. The supplied pressure should be 13 bar. The supplied temperature should be 25 to 50 degrees Celsius. And then it is required to filter the methanol with a duplex filter of 10 micron absolute. By installing a duplex filter, it is possible to change over more or less seamlessly if one filter is full. The purpose of the fuel valve train is to isolate the engine from the pressurized methanol supply systems when not running. Furthermore, connections for nitrogen purging are available. The fuel valve train is a controlled component, and therefore the valve train must be approved by MAN as it is part of our safety concept. Furthermore, it is controlled by our engine control system. The FVT includes automatic shutoff valves, which are pneumatically actuated. The FVT is supplied by Electronic Fuel Tech. Electronic Fuel Tech is at the moment the only approved vendor of the FVT. In their portfolio, they have a 1-inch FVT and a 2-inch FVT for different engine power outputs. The 1-inch FVT will cover engines up to approximately 10 megawatt power output, and the 2-inch FVT will cover engines up to approximately 55 megawatt power output. Due to growing market interest in the methanol engine, we have now considered it necessary to investigate the possibilities of including a 3-inch FVT for larger engine power output than 55 megawatt. And since also 60 bore, 70 bore, and 80 bore engines are now in our methanol portfolio, we may also look into including a 1.5-inch FVT for intermediate sizes. Finally, if water and methanol is chosen as a Tier 3 solution, the FVT will include the water valves marked in the top right red box, valves 860, 861, and 862. This is simply an option. Therefore, the FVT can be ordered and delivered without these valves and later retrofitted. The water and methanol technology requires a water pumping unit. We call this the water injection unit. Its purpose is to ensure Tier 3 compliance by delivering water to the FVT where it mixes with the methanol and is delivered to the engine for combustion and thereby emitting less NOx. The water injection unit pressurizes and delivers water to the FVT at 13 bar. Furthermore, a filter is included to filtrate the water at 10 micron absolute to meet engine requirements. The water injection unit is controlled by our ECS, and therefore we can control the mixture of water and methanol and ensure Tier 3 compliance at different engine loads. The purpose of the nitrogen system is to supply nitrogen for purging of the methanol pipes. We also use nitrogen to run an automatic assembly test or verification test at every startup to ensure that all valves, transmitters, and components are working. Finally, we use nitrogen to tightness test the systems after overhaul or maintenance. The tightness test pressure is 13 bar. Purging pressure is minimum 8 bar, and assembly test pressure is the same as the purging pressure. In some situations, we see that shipyards choose to use 13 bar for all purposes. This would still be in line with our specs, and you would obtain faster purging and startup sequences. A common nitrogen system would be beneficial. However, we require separate nitrogen supplies, supply A and supply B, with separate buffer tank or storage and separate piping. This is why. The purge modes justify the necessity of having a nitrogen supply A and nitrogen supply B with separate buffer tank or storage and separate piping. Purge mode 1 is used during startup and supplied by nitrogen supply B. Purge mode 2 is used during stop mode and supplied by nitrogen supply A. No matter what happens to nitrogen supply B, nitrogen supply A should always have nitrogen available at correct pressure in order to stop or shut down the methanol operation. We will explain how the purge modes are integrated in the different engine sequences later on in the presentation. The purpose of the methanol fuel service tank is to have a dedicated tank to accumulate methanol for engine operation. Furthermore, it should be able to separate return contaminated methanol from the ready supply of methanol for operation. The returned methanol will be contaminated with sealing oil and nitrogen, and the sealing oil will settle to the bottom of the return compartment. The methanol will stay on top and spill over to the fuel compartment to be reused. If the level switch detects the sealing oil, then the return compartment should be drained. With a dedicated methanol service tank with return capabilities, it is possible to completely separate the methanol from the service tank, that is, from the engine, with the methanol from the cargo or storage tanks, thereby not contaminating the cargo or storage tanks. The service tank should also be equipped with nitrogen padding and a PV valve in order to compensate for the pressure or vacuum related to emptying or filling of the tank. During purging, engine operation, and service tank filling, pressure and vacuum is created respectively. This is handled by the nitrogen padding and PV valve. Finally, it is important to include the valves required where valve 836 is necessary for the assembly test in order to start up methanol operation. Our dual fuel system includes double wall pipes on the engine, as well as yard piping downstream the FET, according to IMO rules. The double wall pipes are ventilated with minimum 30 air changes per hour. We require dry air. The outer pipes are outer pipe tested prior to methanol operation. Here you can see the ventilation system. On the left, you see our double-wall ventilation system, including redundant gas detection downstream the engine, redundant flow switches upstream the engine, the ventilation fan, as well as other valves and components for outer pipe testing and air inlet. As mentioned previously, we require dry air for the double-wall ventilation system as shown in the table on the left. Furthermore, for the methanol dual-fuel engine, we require a sealing oil unit, as mentioned previously. This sealing oil unit is ventilated and also equipped with gas detection, ventilation fan, and flow switches. We, however, do not have strict requirements for the air used for the sealing oil ventilation system. I will now take you through some of the sequences of operation for the methanol engine. Firstly, you can see a simple flow diagram for explanation purposes only. This should not be used as design basis. You can see the relevant subsystems, such as the service tank, the fuel supply system, the FET, the nitrogen supply, the water injection unit, and the engine. The first sequence of operation is prior to methanol operation. It is necessary to run an assembly test, also called verification test, in order for our engine control system to allow for methanol on the engine. The assembly test is run using pressurized nitrogen at purging pressure. As you can see, the block valves 801 and 807 are closed in the FET, sealing the engine from the pressurized methanol from the fuel supply system. In order to pressurize the engine and components, valve 836 on the service tank is closed. Once assembly test is passed and all components, transmitters, and pipes are as expected, we can move on to the next part of the startup sequence. The second sequence is the filling scenario. The filling scenario is split into two parts. The first part you see here, where we open the double block and bleed valve arrangement in the FVT methanol line. Block valves 801 and 807 are opened and bleed valve 802 is closed. Keep in mind that block valves and bleed valves always work oppositely in a double block and bleed arrangement. When one opens, the other closes. When the block valves 801 and 807 are opened, the methanol filling process of the pipes and engine begins. We likewise open valve 836 on the tank in order to allow for this filling process. A level switch on the engine return pipe informs us when it measures wet, and thereby that the pipes and engine are full of methanol. Once this occurs, we use the nitrogen B supply in purge mode 1 to purge the return pipe free of methanol back to the service tank return compartment. This is necessary as our safety system on engine requires that the return is liquid free. This is again detected using the level switch. Once the return line is purged, our engine is full of methanol and ready for operation. We are now able to run methanol on our engine. Methanol operation can occur for short as well as long periods, however only within 10 to 100% engine load. At lower speeds and engine loads, it is necessary to change over to fuel oil mode. If we choose to operate the engine in Tier 3 areas, and we have chosen to use water and methanol as our Tier 3 technology, then we start up the water injection unit from our mop screen, the main operating panel. The water is pressurized and delivered to the FET, after which we run a sequence that leads to the opening of the water block valves 860 and 862, and closing of the water bleed valve 861. Now the FET will ensure that methanol and water is mixed in the FET. The engine control system has a safety function that only allows for the water block valves to open if the pressure in the FET water line is measured slightly higher than the methanol. Once we decide to stop running on methanol, we initiate the stopping sequence. This includes closing the block valves 801 and 807 on the methanol line to stop supply of pressurized methanol to the engine. We likewise close the water block valves 860 and 862 to isolate the engine from pressurized water supply. Once both sets of block valves are closed, the pressure on the engine will drop to the service tank pressure, and we then initiate purging with nitrogen. First, we liquid free by pushing methanol and water back to the service tank. We use the on engine level switch in the return pipe to detect when we have freed the engine of liquid. Then we run a short sequence of pulse purges by closing valve 836, pressurizing the engine with nitrogen, and releasing. This gives an efficient and proper purge, leaving the engine free of methanol and depressurized. Here you can see the engine left in its final state, purged and depressurized. It is up to the fuel supply system designer whether they wish to purge the fuel supply system and pipes upstream the FVT at every stop or only in case of maintenance. I have now gone through the presentation about our methanol engine and auxiliary systems. Before we finish, I would like to show you how to access our installation documentation, which includes specifications for the components and subsystems mentioned in this presentation. This will be the final item in this presentation. First, you follow the link in the top left corner given here to find the latest update of our design documentation for yards. You will be granted a username and a login to enter Nexus, and you press the design documentation for yards hyperlink as shown. Then you choose the documents relevant for you. In this case, we have spoken about the methanol engine. So if you look at the blue arrows, it is important to choose low flashpoint fuel related in the documentation group. Then in the auxiliary system, you choose 210069 low flashpoint fuel. And finally, in the low flashpoint fuel type, please choose LGIM. Keep in mind that the documents are provided as information only. The formally valid documents are included in Engine Builder's design specification order. Before you can download the document, please remember to accept the conditions of use by reading and checking the box shown with the blue arrow. Then download the documents. Once you download them, open the compressed file and you will see the following documents available for methanol. Find the relevant document for you and open it. In this case, I have opened the system diagram, named 5589555-1. If you need an overview of what documents are included in the folder, feel free to open the part list shown with the blue arrow. A table of the folder content is available here to see what the folder includes. Keep in mind that when you download this package, you will always be receiving the latest revisions available. This is the final slide today. Before you go, I would like to take the opportunity to thank you very much for your time and patience throughout this session. I would also like to congratulate you for not falling asleep throughout this presentation. My name is Ian Isak Kumaraswamy, and I hope this session and presentation has given you knowledge and understanding of the methanol engine, as well as the subsystems and Tier 3 technology. If you have any questions regarding ME-LGIM and ME-LGIMW, then you are more than welcome to contact me or my colleagues in the Marine Installation Department, and we will be more than happy to assist you in any way we can.